Hi guys, Micah here from EbikeSchool.com, and today I'm going to be showing you how to build a light bulb discharger for your batteries.
Let's pause real quick here. This video got kind of long, partly because I went over a lot of theory and background information in the beginning. If you want to skip through that to get to the building, that's fine. I'm only going to be a little bit offended. So alright, now back to your regularly scheduled programming.
Now, why would you want a light bulb discharger? There's a couple of reasons. First of all, it's healthier for your batteries not to always leave them fully charged. So if you've ever charged your battery up all the way and then find out you're not going to be using it for a while, maybe you're going on a trip or you just don't plan on riding your bike or using your battery for whatever reason, it's healthier for the battery to discharge it a bit. Sometimes it's not always easy to just throw it on your bike and go ride around, so it's nice to have a discharging device that you could use to just drain off some energy from your battery. Now the second reason, and what I use a discharger more for, is actually performing tests on my batteries. And in this way I can determine all sorts of factors. You can find out the capacity of your battery, but you can also look at things like internal resistance, voltage sag under different loads, those kind of things. So it's nice to have a device that can drain your battery under a constant or fairly constant load, so you can test your battery under different conditions. Now I'm going to show you a few different options here. The first is the discharging device I've used for a while, then I'm going to redesign it and build something a bit nicer. But the first option is sort of the quick and dirty option. Now I built this discharger using halogen light bulbs. I like these because they're small, they're powerful, they've got these very convenient sockets, they're just nice to work with. Now these bulbs get super hot, like crazy hot. They're off the scale on my infrared thermometer. It goes up to like 200 C and it can't even measure these. So I don't know how hot they get, but they're crazy hot. So you can't put them near anything wooden or plastic, anything that can catch on fire or melt. So I keep them in this metal mount supported by these vice grips, and I actually use this outside. So I put this on my patio, which is concrete, and I just let it run, and the heat dissipates as the breeze comes through, kind of burns off into the ether. Generally I'm doing 48 volt batteries, so with these four 12 volt bulbs, I just wire them in series. So I end up with a sort of 48 volt lighting system that I can either plug directly into my battery if I just want to drain it a little ways, or that I plug first into a watt meter, and then this watt meter goes into the battery if I want to do tests, which is the more common use for my discharger. I've been using this setup for over a couple of years now. I don't remember exactly when I built this, I think 2.5 years ago, and it just works really well. It's bulletproof. Every time I do a test for a different battery, I just come and I cut the wires and I rewire it. Right now it's actually wired up only using 2 of these bulbs. I was doing tests on 3S and 4S drone batteries, so it's only using 2 of these, and these are actually in parallel. So it's really only using one bulb in series, just 2 of them together. But you can wire this any which way. That's why all these wires are pretty short here, and I've got some tape on some and an alligator clamp on one of them, because each time I just come through and rewire it for whatever I'm testing. But I want to build a new system, something that's easier to use and more user-friendly, and something I don't have to rewire each time that I want to use it. And so I'll show you a couple of my sort of failed experiments along the way, and then I'll let you follow along while I redesign and rebuild a new one. Now my first redesign was this guy. I've already taken it apart so it doesn't look so great, but essentially this was the lid of a pot, and I had all of these halogen bulb sockets down here. I put this down in a pot with a bunch of holes in it, and I had an exhaust fan up here. And I had this nice switch here that I could sort of switch between from 12 all the way up to 72 volts, selecting how many of these sockets I had in series. And the problem was I was trying to contain the heat in this thing and use an exhaust fan to sort of suck the heat out the top, and it didn't really work. At lower power it was alright, a few hundred watts it could handle. But once I got up to 1,000 watts, this thing just got too hot, and I realized I shouldn't try to play the game of trying to contain the heat. I should just stick with the method I was using before, with letting the heat sort of dissipate and use it outside. So I sort of threw this design out the window and started on something else. This was my next design. I made this out of 2 electric bicycle cases. Actually, this was a bottle battery case I cut in half, and this was a rack battery. And the idea is I've got 2 sets of these halogen bulb sockets here. Both of these are in parallel, and so I can run anywhere from 12 up to 72 volts. And then this whole thing sort of folds down, and the idea was that it would collapse to be sort of a smaller package. I could, stick it in a drawer, and this would fold up to be out of the way to keep the light out of your eyes while you're working on it. But the whole thing ended up being a lot bigger and less nice and professional than what I wanted. The design kind of went a different direction than I was hoping, and I gave up on it partway through and just decided to start over. So I'm going to take some of the parts from this on my new build, but I want to build something nicer. So this is what I'm going to do on my next build, which will hopefully be my last build. I've got this toolbox, and I like this because what I want to do is I want to mount the bulbs on the lid here, and then when I open this up, I can have the bulbs when they're running facing away from me. That's one of the problems with the previous setups, is the bulbs are like right in your face, so you're trying to write down data, and you're going like this, trying to not get blinded by these crazy bright bulbs. So the bulbs on the back here, and they'll face away from me while it's running. And then on the inside, I can have all my wiring, my meter, my auxiliary battery to keep the meter running. And I can just keep this looking a lot nicer, and then when it's done, I can take the bulbs out, I can keep everything inside of here, and just have it as a nice, storage box for everything. So I think this is going to be a better method, and so that's what I'm going to build today. Now I'll show you how I'm designing this to work, and you can follow along and build your own halogen bulb discharger in the same way. So let me get my paper out here. I like to start just designing these things on paper. For me, it's just easier to draw this stuff out. It helps me think about it, but if you like to use whatever drafting program or just start building, whatever works for you. Let me show you how I do this. Alright, so here's the circuit I've set up. I apologize in advance if this circuit isn't really drawn the way the normal conventions are. I'm a mechanical engineer, not an electrical engineer, and I just sort of learned circuits from a single class and looking at drawings that other people have done. Essentially, this is the idea. Each of these resistor marks here is going to be one bulb, so I'm going to have 2 parallel strings here with 4 halogen bulbs each. And the idea is that I'm going to have a switch coming from my battery, that the switch can switch between 48, 36, 24, or 12 volt configurations. And it just basically decides where the positive end of the battery comes into the circuit. So like right now, the switch is set on 48 volts. So it's using this entire string of series bulbs, but if I were to say switch this to 36 volts, if I went straight up to here, then we'd basically be cutting out these 2 bulbs here. We'd come in right here and we'd be using the first 3 bulbs in each string. The other thing is that I don't have to use both of these parallel strings. I can just put a bulb in these 3 sockets and ignore these 3. So having 2 parallel strings allow me to add twice as many bulbs to have twice as much power draw. But I don't have to use all those. And then again, I can just, I can set this to 12 volt and just do, 3 or 4S batteries, like drone batteries, and my circuit will basically just come straight up to the first set of bulbs and then out back to the battery. So that's the way this is set up. This circuit right here would just be a circuit set up to drain the battery, but if I want to use this meter that I've got here, basically I would just add this into the circuit. I don't know if you could hear that plane going on overhead. Sorry about that. But essentially I would just come in here, I would add in my meter, and this meter would then go back out into the circuit like this. And so this is the way I'm actually going to set up my halogen bulb discharger that I'm going to build right now. So this is the plan. If you wanted to go up to 60 or 72 volts, you could do that. This specific meter only goes up to 48, so you need a larger meter or cycle analyst to do more than 48 volts. But you can also do 52 volts here. I think you can actually go up to about 60. But this is the circuit I'm going to use. So let's get started building.
Now the first thing I did was measure out and then drill the holes in the lid of the toolbox for the wires to pass through, and then place the sockets and the wires through those holes. I'm cutting these sockets off of the last project I worked on, so these wires are a bit short, but it'll still work out just fine. Once I got all of those sockets in the lid, I started soldering up the negative end of the first 2 sockets, as you can see in the diagram here. And then I slid some heat shrink over the solder connection. Now I was too lazy to go and get my heat gun, so I just used a lighter that I had laying around, but you should really use a heat gun on these things. Then I made my second set of solder connections between the first and second set of halogen bulb sockets here. And then I just labeled the end of that first 12 volt wire so I don't get confused when I have a few of these wires in the end. Next I did the third solder connection, which is between the second and third set of sockets, and I had to add an extra length of wire here just to make sure these wires were long enough to reach. But then when I did the solder connection between the third and fourth set of sockets here, all the wires were long enough, so I just soldered those all straight together. And then lastly I soldered these final 2 wires here. These are the positive ends of the last set of 2 socket holders here. and these are just going to run down to the 48 volt setting on the switch. And then because my wires are starting to channel Medusa here a little bit, I decided to use some of this nylon braided cable sleeve to neaten it up. Now here's a cool trick. You'll notice the ends of this stuff fray immediately when you cut them, so if you just use a lighter, you can melt the ends and then they'll stop fraying instantly. And then I just slid that braided cable sleeve up over my wires, and it really makes the stuff look a lot nicer and neater. Next I drilled a hole for my multi-position switch here, and this is what's going to allow me to select between the 12, 24, 36, and 48 volt settings. I'm going to connect those red wires into this switch in just a minute. Now I wire my 12 volt wire onto that first terminal of the switch there, and then I'm just going to follow along and wire each of these successive wires onto the terminals, and that's going to allow me to select between these positions. Now that black wire is the negative of the entire halogen bulb array, and that's going to go straight to the meter. I added Anderson power pole connectors to connect the switch to the load side of the meter, and then on the source side, that's where I'll plug in my battery that I'm testing. Now I've got these alligator clip leads going to the auxiliary power supply on the meter itself. This way I can plug in a battery, which I'll use an 18650 cell, to power the meter so it runs even when my test battery dies. For this auxiliary battery, I'm just going to spot weld some tabs onto an 18650 cell here. I need to check what the minimum voltage is for that meter. I think it's actually something like 3.5 volts or something, so this is about the minimum that you can power it with, and if anything, when this battery gets low it might be too low, so I need to make sure this battery stays fairly charged, but this should work for powering that meter even when my main test battery dies. Now I'm going to slide a piece of heat shrink over this battery because I've got these exposed terminals on it now, these tabs. I don't want them to touch the inside of the toolbox if it ever scrapes off the paint and cause a short, so that heat shrink should protect it. And now that the heat shrink has shrunken, it's covering the ends of those tabs, and I don't have to worry about creating a short. The alligator clips can get right in there and connect to that battery. And this is obviously a very crucial step. I have to handwrite on my voltage labels onto this switch. So I'll number these 12, 24, 36, and 48 volts, and now I have a cool little selector switch.
Alright, so now I've finished my discharger here. I'm actually pretty happy with how it turned out. I've got on the outside here all of my sockets, so I can do 2 sets of up to 4 halogen bulbs on each row. And then on the inside, I've got storage for all my halogen bulbs, my 18650 that's going to be my auxiliary battery for running my meter, and my watt meter here. Then on the side here I've got this nice little switch here that allows me to switch between 12, 24, 36, and up to 48 volts. So let's go give this a try. Oh, before we go run this on a battery, I'll just explain how you control how much load you're putting on a battery. So I've got here, let me pull these out. I've got mostly 50 and 100 watt halogen bulbs here. You can also use 20 watt, which are pretty standard, but there's just not a lot of power there, so you need many parallel strings. When you use 50 or 100 watt, it just means you need fewer bulbs. So to determine the current that you're going to run on your battery, you just divide the voltage over each bulb by the wattage. I'm sorry, you divide the wattage by the voltage. So that's going to get you your current. So for example, let's say I want to run a 48 volt battery. I'm going to put 4 bulbs in a row here. So it's going to be 48 volts. And I'm going to use, let's say 400 watt, that'll make the math easier. So I'm going to have 400 watts divided by 48 volts. It's going to be about 8.5 or so amps. You can also do it per bulb, so you can say each one of these is going to be carrying about 12 volts. 100 divided by 12, again it's about 8.5 or so. If I used 50 watt bulbs instead of 100, I'd be at about 4.25 or so. I'll put the math up here somewhere and put the exact numbers. But that's the idea. And you can also sort of mix and match. Let's say I want to do higher current. Because I have 2 sets of parallel sockets here, I can run 2 sets of 100 watt bulbs. So instead of that 8.5 or so, I'd be up around 17 amps. Or I could run 1 set of 100 watt and 1 set of 50 watt. That's going to put me around 12-ish amps or so. So you can play around with the wattage in the different parallel strings here, and that will let you sort of dial in your current. One last thing to note, your current isn't going to be constant. It's going to actually decrease slowly as the battery drains. And the reason for that is basically Ohm's law, where you have I equals V over R, And as the V decreases, if R is staying the same, then I is going to have to decrease as well. So as voltage decreases, current decreases. It is going to be a decrease in current, but it's going to be a fairly constant decrease in current, which is still useful for a lot of these measurements. All right, now let's go take this outside and run some tests. All right, now I'm going to be doing these tests outside. I could probably do it inside. I built this tester with the bulbs fairly high, so I don't think there's going to be a lot of heat on my work surface, but just in case I'm going to do it outside, also have a breeze and better heat dissipation. This first test I'm going to be doing with a 48 volt 10 amp hour battery, and so I've got 8 100 watt bulbs up here. This is going to give me an average of about 17.5 amps or so. So this is going to be about a 1.7 C, a fairly intense test for this little battery. So we'll be able to see what kind of condition it's in. Now I've got my meter already connected to my auxiliary battery here, so I'm going to go ahead and plug it into my battery that I'm testing. Let the motorcycle go by. I'm going to have my switch here set to off when I connect this, so the test isn't going to start yet. Now if I take a look at my meter, here we can see that we're about 54.5 volts, and right now we're at 0 amps. We haven't started the test yet, so let's go ahead and start this test. So when I flip this switch, we should be starting. And there we go. Those are bright. Alright, also kind of hot. I can already feel the heat on my fingers here. So the test is going. Let's look at our data here. So I see 48.9 volts at 17.26 amps. So we can calculate the voltage sag from our battery by subtracting the voltage that we see under load from the voltage that we started with. So let's see, we had here 54.52 volts, and we'll subtract 48.9, which will give us approximately 5.6 volts is our voltage sag. Next we can calculate, or we can sort of roughly approximate our internal resistance using Ohm's law. Now you remember Ohm's law is I equals V over R, current equals voltage over resistance. So if we're looking for resistance, R would equal V over I. So we can take our voltage sag, V, and divide it by our load at that point, I. Let's see, so that would be 5.6 volts divided by the current we had was 17.26 amps for that voltage sag, which gives us 324 milliohms of resistance. That's the internal resistance of the battery, which is actually fairly high. This pack is about 1.5 years old, and it's built using 4, I think it's Samsung 26F cells in parallel, which even for that, it's a bit high. So this pack is not, I can already tell it's not in a great state, but we'll see what the test shows us in terms of its capacity and what it looks like. So this is a rather interesting occurrence that I didn't foresee. The hot glue that I just secured the backside of those wires with is melting and running down the inside of the box there. I guess that's not really a problem. I just should have realized that a gigantic heat source on the other side of a metal hot glued surface would do that. But it's interesting, the things you learn after you build something. Alright, so I just hit the low voltage cutoff on my battery's BMS, and my meter here says that I got to about 10.18 amp hours, which this is actually a 10.4 amp hour battery, so that's really quite good. That's about 97% capacity after 1.5 years. Granted, I haven't used this battery that much. The resistance was a little high, but it seems to have still retained its capacity quite well. So I'm pretty happy with this. The next thing that I want to do is I want to test actually a drill battery. So I've got my cordless drill here. This has a 3S, so a 3-cell battery, which is rated at 11.1 volts for 3 lithium cells. I'm not sure what cells are in here, but I can test this very easily by just running my light bulb discharger on the 12 volt setting. 11.1 volts, very close to 12, so this is going to work just fine. I've already gone and I've removed all of the bulbs except for one 12 volt bulb here. I'm going to leave this at 100 volts. At 100 watts. I think that's probably a reasonable amount for this power drill. These don't have any rating on them to let me know what kind of wattage. Yeah, it doesn't say anything about the wattage of the drill, so I think 100 watts is probably reasonable to do this test. And I made up these little test strips where I just put alligator clamps on some nickel strips. So I'm going to plug these into my battery here. And I have my switch here set for 24 volts right now, which is basically off since I don't have anything in the 24 volt sockets. So I can connect my meter to my drill battery using these alligator clamps.
So let's fire this thing up. If I switch it to 12 volts now, we should get light. And there it is. Alright, let's flip that back up so I don't blind myself again. Alright, so 8 minutes later, my meter shows me that I got about 0.975 amp hours out of this drill battery. It doesn't say anywhere on here what it's supposed to be. I read that these are 1.3 amp hour. If that's the case, then it means I'm already down to about 75% capacity compared to when it was new, which is not super great. But you know, at least now I know. So that's how this works. You can test all sorts of batteries this way. And if you end up building one yourself, then I'd love if you'd share it with me. You know, send me a picture, show me how it turned out. One last thing, I've been getting a lot of questions on my YouTube channel, which is great, on all sorts of topics, and I try to answer them in the comments section, but I thought it might be interesting to maybe make a Q&A video that I've seen some other how-to people on YouTube do. So if that's something you guys would be interested in, let me know and we can do a Q&A video. So thanks for watching, and hope you learned something.